Afternoon, ladies and gentlemen. My name is Tran Vu and would like to talk about my paper for EUMETSAT Conference 2021 entitled A New 3-Day Observation of Convective System Dynamics Using Multiple Satellites. First of all, this is a summary of the presentation, including 4 sections. First, we talk about the 3-day semantic observation of decompression and vertical horizontal dynamics. The combination of LEO and GEO satellite to observe the decompression. We also present the estimation methods of convective windows from C-band Sentinel-1 SAR and L-band smart radiometer radar. Second, we present the interview result of convective system by the combination of Sentinel-1, EULIS, and EUMETSAT. Third, we illustrate the combination of Sentinel-1 and SMART to observe the movement of the surviving pattern associated with the decompression. Finally, we talk about the conclusion and perspective. Now, this slide presents the 3-day semantic observation of decompression and vertical and horizontal dynamics. As you can see, the hot air represented by the intense updraft, it contributed to the formation and development of the deep convective cloud. The hot air is then cooled and become heavier and finally move toward the surface. This is also called downdraft. If the thermodynamical conditions at the mid-level are favorable, the downdraft becomes more intense. When they hit the sea surface, they may induce wind gusts that can be estimated from the data observed by Sentinel-1 and the other devices like radiometer or scatterometer. Now, thanks to some matching in footprint of EUMETSAT, EULIS, and Sentinel-1, we can combine the 3 devices to observe a deep convective cloud, intense downdraft, and surviving windows respectively. So now let me talk about how to be able to estimate surviving spectrum SAR and radiometer radar. On the left, you can see here via radar signal, we can receive backscattering or normalized radar recession from sea surface roughness that is strongly impacted by surface wind. The relationship between surface wind and radar backscattering can be described through geophysical model function. In C-band, it's called CMOD, and this paper uses CMOD by N for surface wind estimation. And now on the right, the L-band smart radiometer instrument will measure brightness temperature of ocean surface also conducted by wind. The obtained data are used to calculate the difference between brightness temperature of ocean surface and that of flat ocean surface. The latter is not impacted by wind. Then the difference in brightness temperature is applied to the radiative transfer model to estimate surface wind speed. The detail of the 2 models can be found in the reference sheet in our paper. So we have explained in the previous slide how to estimate surface wind speed from SAR and radiometer radar. Now we would like to talk about the estimation of convective wind gusts from satellite. First, why satellite? Because they have some interest, a high spatial resolution and wide swath that can offer the observation of convective wind pattern at various scales. For many years, the interpretation of the high intensity radar backscattering on-site image is an interesting debate scientific subject. Indeed, we can lead here 3 assumptions to interpret this feature. Rainfall effect on the sea surface, hygrometer in the melting layer, and convective wind gusts up to 25 or 30 meters. Many papers in the literature have indicated that the C-band radar backscattering is almost not impacted by precipitation. And then we can estimate it, surface convective wind gusts from C-band Sentinel-1 image. We are presenting here 2 interesting Sentinel-1 image showing the presence of surface convective wind gusts. They tend to move westward, as you can see here. Also, I would like to say that survey convective figures can be estimated from the urban smart data. Not that everybody accept that the urban radar signal is not impacted by rainfall, and then the similarity between wind speed estimated L-band and C-band will strengthen our assumption that supply convective figures can be estimated from C-band Sentinel-1 image. So applying the proposed method in the reverse line, now we are presenting in the multi-view result of the convection based on the combination of Sentinel-1, ALUS, and METEOSAT. The first case illustrates an observation of a cellular convection. Why this case? Because it shows the sensitivity of Sentinel-1 to detect convective wind. Indeed, as you can see on the left, is by the small scale of the display convective wind pattern, we can observe wind associated with deep convection. METEOSAT and Sentinel-1 show that the supply wind pattern and deep convecting cloud have the same location. In particular, the Sentinel-1 wind hotspot corresponds to the coldest cloud section. On the right, we can see that the intense LoRa with very high vertical wind intensity can be measured by ALUS meter. They have the same location as a subscribing pattern and its convective cloud. This offers a strong link between three events observed by the three devices. So as well as the reverse case, this one presents the detection of subscribing pattern associated with a small cellular convection from Sentinel-1 image. They correspond to the deep convecting cloud observed by METEOSAT. And more interestingly, when we observe the ALUS data corresponding to the Sentinel-1 and METEOSAT image, we only see an intense LoRa backshot, and it matches the subscribing pattern and deep convecting cloud. So now we are moving to observe mesoscale convective system. We see that the surface convective wind pattern on Sentinel-1 and deep convecting cloud detected by METEOSAT have the same location. Likewise, the corresponding ALUS data show the vertical wind representing turbulent zone at the mid-level with many intense LoRa and updraft. The missing data indicate are due to the dense water cloud. In particular, the intense LoRa as the near sea surface match the Sentinel-1 wind hotspot and the coldest cloud section. When observing the METEOSAT image, we see that the deep convecting cloud move very slowly, probably due to the low wind intensity at that level. Meanwhile, the coldest section changes very quickly. So in this slide, we are presenting another case of the mesoscale convective system observed by Sentinel-1, ALUS, and METEOSAT. This case is interesting because we can observe the wind front and then can assume that these convective winds tend to move slightly the southwestward. In fact, when we see the corresponding METEOSAT image, we note that they also tend to move toward the southwest. The convecting cloud in this case seem to move faster than those at the reverse case. So they indicated in the reverse slide, in addition to Sentinel-1, we can estimate the wingers from the urban smart radiometer data. Here is the observation of the surface wind pattern on Sentinel-1 and SMAP image on 1st April 2017. This surface wind pattern is detected on Sentinel-1 image as about 5:14, while this one is observed by SMAP about 15 minutes later. And both of them have a close form. Despite having a large spatial resolution, we can see the strong surface wind zone with the 15 and 17 meters per second on the SMAP image. And when comparing the location of surface wind pattern on Sentinel-1 and SMAP image, we can note that this one tends to move southwestward. As expected, the convective winds on Sentinel-1 and SMAP image have the same location as the deep convecting cloud detected by METEOSAT. In particular, they have also the same movement direction of southwest. So in conclusion, the combination of LEO and GEO satellite, which means Sentinel-1, ALICE, and EUMETSAT, offer a 3D view of convective system and also strengthen the semantic understanding of deep convection, and particularly the assumption of the high intensity radar backscattering induced by convective windows. Additionally, the combination of C-band signal one side and L-band map the radiometer bring the observation of the convective wing pattern movement. The latter have the same direction and maybe velocity in the deep convective cloud. Also, this paper proposes some perspective to improve the forecast of the convective windows based on side image. So thank you very much for your attention.